we're just going to run through the last 3 examples that we didn't have time for during section. So the first one of this is from section 4.4. We want to find 3 things. We want to find the set, which we call S, of subsequential limits of our sequence Sn, and also the lim inf and the lim sup of Sn. And Sn is this sequence. It's 5 plus -1 to the n plus this thing, which is 2 times -1 to the floor of n over 2. So let's get a little more intuition for this. Let's call 5 an, -1 over n is bn, and this fancy thing is going to be cn. So an, we know what this is. It's 5, 5, 5, 5, 5, etc. Okay, bn is also not so bad. -1 to the n. So if the first term is going to be -1, 1, -1, 1, -1, so on, and it keeps alternating. And Cn, okay, well, let's think about this. So when n is equal to 1, we take 1 over 2, we take the floor of that, which is 0. So -1 to the 0th power, which is 1, we multiply it by 2. When n is 2, n over 2 is equal to 1, so we take the floor of that, it's 1. And so we do -1 to the first power, which is just -1. Again, we multiply that by 2, so we get a -2. And then our third term is n is 3, so we get 3 halves. Take the floor, we get 1 for a second time. And so this is the same as the second term. So it's -2. And then when n is 4, this is 4 over 2. We take the floor, it's still just 2. -1 squared is 1 times 2 is 2. And the fifth time, again, is the same. We take 5 halves, n is 5, so 5 halves. The floor of that, we get 2. -1 squared times 2 is equal to 2. And so you'll just notice if you go out a few more terms that this just repeats twice. Maybe I'll even write those in. So we would have -2, -2, 2, 2, -2, -2, 2, 2, etc. forever and ever. So we don't care that much about the specific terms, except just notice that we get all the possible combinations here. We get 5, -1, and 2. We get 5, 1, and -2. We get 5, -1, and -2. We get 5, 1, and 2. And those 4 things are going to repeat indefinitely. So essentially, we're going to have 4 subsequential limits. We either have the most negative one, which is 5, -1, and -2, which is equal to 2. Or we can have 5, -2, and +1, which gives us 4. Or we can have 5, +2, and -1, which gives us 6. Or all 3 can be positive, which gives us 8. So I do think this is kind of cool. We get 2, 4, 6, and 8 as our limits. And so what is the lim inf and what is the lim sup? Well, they're just the inf and the sup of S. So lim inf of Sn equals inf of S, which in this case is just the minimum, so it's 2. And the lim sup of Sn is the sup of S, which is 8. Okay, now let's do something from 5.2. We're going to do use the trickiest continuity definition from 5.2. So use the open set definition of continuity to show that F R to R, which we're going to define like this. And I took this straight from the book. So if you want to look at it, it's towards the end of this section. So this function is not continuous. Okay, remember open set definition is F is continuous if and only if let's just say F goes from R to R. That'll just to make it easier. No, let's say from A to B. I think is continuous if for all open subsets U of B, when we take the inverse image, it's still open. So that's now a subset of A. That's still open. So we're going to contradict that. Let's look at what this function looks like. Oof. Okay, so if x is greater than 2, then we just get 4. And otherwise we get x. So looks like this. And so obviously this isn't continuous, but what we're going to do is we're going to choose a particular open set that's going to include this jump, and that's going to be a problem for us. So let's have our open set in B, which is the image, so it's the y coordinate. Let's have it go from 1 to 3. Okay, so let B be the interval from 1 to 3. What is the inverse image of that? Well, we look, where does it hit this interval? So everything up to 2 and starting with 1. Okay. Oh, sorry, I got this wrong. This should be, yeah. So it's x if x is less than or equal to 2. So this should be, this is very important. This one should be open and this should be closed. Okay, then, sorry, this is U. Then F inverse of U is all of the points that map into that set, which are just the interval from 1 up to 2, including 2 but not including 1. So this is not open. So then F is not continuous. Okay. So this is how it works. And I might invite you, if we had this point instead being up here, what open set would we choose? That's also not continuous, but which open set will we choose to ensure that we can see that? Okay, so now on to the final question, which is 5.1. So we're going in reverse order here at the end. So prove using the definition of the limit as x goes to 1 of x squared plus 3x minus 4 over x squared minus 1 equals 5 over 2. Okay. Now, if we had to get the 5 over 2, you'll see a point in the proof where we kind of would need to would be able to find it if we didn't know. We would just leave this part blank. So I'll talk through this. So first we note that x squared plus 3x minus 4 factors is x plus 1, x minus 4, and x squared minus 1. Well, that's a difference of squares, is x minus 1, x plus 1. So as long as x isn't 1, we can simplify this fraction. So let's let epsilon be greater than 0, and let delta be the minimum of 1/2 and 2/3 epsilon. So delta is always going to be a minimum. The 1/2 is going to help us kind of bound something, and then the 2/3 epsilon is what we're going to get at the end. But as usual, we could figure this out in reverse. So then if x minus 1 is less than delta and not 0, then what do we get? So we take this function, 3x minus 4, x squared minus 1, minus 5 halves, equals, okay, so because x minus 1 isn't 0, x isn't equal to 1, so we're allowed to divide both top and bottom of this fraction by x minus 1. Let's do that. So we get x plus 4 over x plus 1 by the previous calculation, minus 5 over 2. And so when we add this in, we get minus 3 halves x minus 3 halves over x plus 1. And so now let's pull out the negative 3 halves. It's an absolute value, so it's going to become positive when we pull it out. 3 halves absolute value of x minus 1 over x plus 1. Okay, so here's where we get the x minus 1 on the top. That's very important. So how do we find the 5 halves? I think one thing is we know we're on the right track when we get this. So if you've just guessed at random, then here is the spot where we know that we're in luck, because we know this is going to be very small. But the place that I would like to do it is right after we've canceled this. If you look and you plug in for x, if you plug in x equals 1 here, in this thing you get 5 over 2, right? 1 plus 4 is 5, 1 plus 1 is 2. So that's how I figured out the 5 halves. So I would suggest you kind of do that. What I did when I originally worked this out is I left this blank. And then when I got to this point, I was like, oh, it's going to be 5 halves. Just like we usually do for our delta. Okay, so now x is, we have x minus 1 is less than or equal to delta. So x is between 1 minus delta and 1 plus delta. Now delta is less than or equal to 1/2. So x is bigger than 1/2. And so x plus 1 is bigger than 1.5. So in particular, for sure, this is x minus 1 over 1, right? We've made the bottom bigger. Sorry, we made the bottom smaller, so we made the whole thing bigger. Okay, and so x minus 1 is less than delta, so this is less than 3 over 2 delta. And this is equal to epsilon. And therefore, this limit is this. So how did I find these things? Well, again, the 1/2 I kind of found. I could have made it 1 maybe, but I wanted to bound this x plus 1. And so I wanted x to be close enough to 1 so that x plus 1 was going to be bigger than 1. And then the second thing is we got to here 3 over 2 delta, and I just wanted that to equal epsilon or be less than epsilon. And so this should be less than or equal. I just said that epsilon is 2/3 delta, so that delta is less than or equal to 3/2 epsilon. Okay, so that's it. That's the rest of the problem. So I hope that was helpful.